Okay, so I'm going to try to get us caught up with where we should be in lecture with these videos. So I'm going to go about as far as I can to the end of this presentation, and then we'll cover the remainder of chapter 15 on Friday, okay? So last Friday, we were looking at the beginnings of equilibrium, right? So what's equilibrium? The rates of the forward and reverse reaction have equaled each other at equilibrium, and so at that point in time, the concentrations of our reactants and products no longer change. And so we can quantify the magnitude of equilibrium, I guess more importantly, like who predominates at equilibrium, by something called the equilibrium constant, right? And so the equilibrium constant was given as our law of mass action. It was just the concentrations of our products, right? So products come first, that's in the numerator, raised to their stoichiometric coefficient. So whatever number is in front of each one, that's what number goes out in the exponent, divided by the concentration of reactants, raised to their stoichiometric coefficients, right? And so what's important about this is that these concentrations have to be at equilibrium, right? So we're measuring these concentrations and we're plugging them in to the equilibrium constant expression by measuring these values at equilibrium. Also, for Kc, this is a particular equilibrium constant. These guys are measured in terms of molarity, and so they're measured in terms of moles per liter, okay? All right, so that's Kc, and that's what we've been dealing with. We went through all the various things that you can do to Kc with respect to multiplying a reaction by a number, what do you have to do to K, etc. And there's one more relationship that we have to derive, and that is the relationship between Kc and a different equilibrium constant called Kp. Okay, so Kp is the exact same concept. It's the products raised to their stoichiometric coefficients divided by reactants, except instead of these guys being measured in terms of concentrations, in Kp, these guys are measured in terms of partial pressures, right? So it's all of our reactants and products measured in partial pressures as opposed to concentrations, okay? So Kc, Kp, they're the same thing, except we're just differing the ways in which we measure our equilibrium values for our reactants and products. For Kc, we're measuring these in terms of molarity, and for Kp, we're measuring these in terms of partial pressures, okay? So can we relate Kc to Kp? Well, we can, because concentration and partial pressure are kind of proportional to one another, and we can convert freely in between the two, okay? So how do we do that? So this guy comes back to the ideal gas law. Okay, so the ideal gas law is right here, PV equals nRT. And so P here is pressure, V is volume, N is the number of moles of gas, R is our ideal gas constant, and then T is temperature, and this is in Kelvin, okay? So, just as a reminder, concentration is defined as number of moles divided by volume, and so we can essentially factor out or divide out a concentration in terms of the ideal gas law. So pressure is equal to concentration times R times T, so times the ideal gas constant times temperature. So we can rearrange things and we can define the concentration in terms of partial pressure, okay? So yes, concentration and partial pressures, they are directly proportional, and we can determine one from the other. So then we're going to take this and we're going to plug it into our Kc expression, okay? A bunch of math is going to occur. We're going to factor things out. We're going to cancel things. And long term, we're going to be left with this equation, which is Kp is equal to Kc times RT raised to the n, or the delta n power. Okay, and I'm going to talk about what delta n is here in the next slide. Okay, so Kp is equal to Kc times RT raised to the delta n. So what is delta n? So delta n is essentially determined by the number of moles of gas of product, right? So this is number of moles of gas as a product, and you're subtracting from it the number of moles of gas as a reactant. So this is the number of moles of gas as a reactant, okay? So it's the difference in the number of moles of gas between the products and the reactants, okay? So there is a special little occasion where Kp essentially reduces down to Kc. So let's say that we had a chemical reaction where you had 3 moles, so number of moles of gas product, let's say this guy was equal to 3, and then number of moles of gas as a reactant, let's also say this one was 3, right? So for delta N, we would have our products first, so 3 minus 3, which would give us 0. So we plugged in delta N equal to 0 into our little Kp expression, then we'll find that RT raised to the 0 just ends up being 1, and Kp reduces down directly to Kc. Okay, so this is a special little occasion where they're equal to one another, and it's when the number of moles of gas don't actually change in the reaction. Okay, so how would you guys actually go about using this? So let's say you have a reaction. So we have 2 NOs combining with an oxygen to form 2 NO2s, and they have given us the value of Kp for this reaction, and they want you to determine the value of Kc, okay? So we're going to use our little equation that we just derived, that Kp is equal to Kc times RT raised to the delta N, and I'm going to rearrange this to solve for Kc. So Kc is equal to Kp over RT delta N. It's important to note that that delta N goes specifically only with the RT. It doesn't go with the K, right? So it's delta N, or it's RT raised to the delta N, okay? So now I've got my Kp. I have this number here, so I can plug that in. I'm going to look at what delta N is here. So delta N is the number of moles of gas as a product. So the product comes first. If I look over here, I only have 2 moles of gas as a product. So 2 minus the number of moles of gas as reactant. So over here, for my reactants, I have 2 moles of gas plus a 1 mole of gas. Okay, so this is 3 overall. So delta N for this reaction is going to be 2 minus 3, gives us a minus 1 value. Okay, so now I think I have everything. The only thing to note here is that because this comes from the ideal gas law, R takes on the numerical value of 0.08206, and the units here are atmospheres times liters over moles times Kelvin. We use this numerical value of R because we're dealing with partial pressures in atmosphere specifically, and volumes, etc., in liters, moles, Kelvin, blah, 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 okay? So this is the numerical value of R you have to use. Also, again, the temperature has to be in Kelvin, so it's at 25 degrees Celsius. So 273 plus, why does it do that? Why does it do that some days? It doesn't do it others. 273 plus 25 gives me 298 Kelvin, okay? So now I can go ahead and plug everything in and solve for Kc. So Kc is going to be equal to 2.2 times 10 to the positive 12th divided by, I'm going to put this in brackets, 0.08206 times 298 raised to the minus 1 power. So then multiply everything out, and I end up with a Kc equal to 5.38 times 10 to the 13th. And so that would be the answer for that type of question, okay? So go through that, make sure that you've got the math correct and you're getting the exact same answer as I do. Okay, so then for this question, this is what's going to be on the video assignment. I'm not going to go through the answer for this. I give you Kc for a reaction, and I want you to calculate Kp for this reaction at 25 degrees Celsius. So again, you may want to try this before you go on to take the video quiz assignment, but this one will be on there. Okay, so we've been looking at our equilibrium constant expressions, right? So if I had a reaction like this, my equilibrium constant expression would be K, and we'll say we're dealing with concentration, so we'll say Kc is equal to the concentrations of my products. So I have CO2 to the 1 power, so we can just leave it as CO2, times carbon over the concentration of my reactants, which is CO, and this is raised to the 2nd power because there is a 2 in front, okay? So equilibrium constant expression for this reaction should look something like this, okay? Now note that one of our products here is carbon, so it's solid carbon, okay? And we have to think that in these chemical reactions, what we're dealing with respect to Ks is we're dealing with changes in concentrations, changes in partial pressures, etc., right? So if we have something that is a solid that's part of our reaction, is it going to change concentration at all throughout the reaction, right? So let's say we start with no or like a little bit of carbon. Let's say like we have a little bit of solid, 5 grams of carbon, and as the reaction progresses, let's say we make 10 grams of carbon, right? So we do make stuff, but overall, how do we measure the concentration of a solid substance, right? We don't really measure concentration. Instead, we measure something like density, which is the amount of mass per volume, right? But as we move through a reaction, as long as we have some solid, the density is not going to change, right? 5 grams of carbon has the exact same density as 10 grams of carbon, right? So because of that, because density no longer changes or doesn't change throughout a chemical reaction, as long as you have some solid in a reaction, its concentration is going to remain constant, even though you are making it and utilizing it, okay? So because of that, we don't include solid carbon or solid substances at all, anything that has a physical state of a solid in our equilibrium constant expressions, okay? So for this reaction, we would ignore the solid because its concentration doesn't change, and the correct expression for this would be just the concentration of CO2 divided by the concentration of CO squared, right? So this is the correct equilibrium constant expression for this reaction. Okay, so this is what we call heterogeneous equilibria. We are dealing with reactants and products that are in different physical states, right? And so what do we deal with that when we're talking about equilibrium? So for the most part, forever and ever and ever, if there is a solid, you're not going to include that in your equilibrium constant expression, and it's not going to change concentration. Okay, so same thing with liquids, with pure liquids. So anytime you have anything with the parentheses little l, right? So if it's pure liquid, you're also not going to include those in any equilibrium constant expression. Again, the reason why is very similar. For water, this is again a pure liquid. For water, water has a concentration of 55 molar, right? So as a reaction progresses, this is not going to change very much at all, right? Comparatively to the total concentration of water, its reaction or its concentration is not going to change in a chemical reaction. So again, we just kind of ignore it. It gets factored in to the equilibrium constant expression already, right? So we do not include pure liquids in equilibrium constant expressions as well. So for this reaction, because of that, our Kc for this, man, I don't know what's the problem today. So Kc is equal to the concentration of our products, so H plus times HCO, this is a C, is that HCO3 minus, divided by the concentration of our reactants. Again, we're not going to include water because it's a pure liquid, so this is just going to be over CO2, and everything's raised to the first power. Okay, so we don't include pure liquids. We do not include pure solids in our equilibrium constant expression. Okay, so now we're going to talk about, we've talked about kind of like the overall idea behind our capital K's, our equilibrium constants. We've talked about kind of how we can relate the magnitude to who's preferred at equilibrium. All right, so if we have a K that's a big number, like greater than 1, products are going to be predominant at equilibrium. A K that's, let's say, less than 1 tells us that reactants are going to predominate at equilibrium. So now we're going to talk about how do we actually get these equilibrium constants, right? How do we determine the actual numerical value for K? Okay, so I'm going to present you 2 different routes to do this. First one's going to be the easy one, and then the second one's going to be a little bit harder, okay? So in the first route, how we determine these equilibrium constants is by knowing all of the concentrations at equilibrium, right? So let's say that we had a reactant or a reaction where we have H2 combining with I2, making 2HI. The equilibrium constant expression for this is Kc is equal to HI squared over H2 times I2, okay? And again, these concentrations have to be at equilibrium, right? But if we are given all of the concentrations at equilibrium, which we are, assume at equilibrium, that H2 is this concentration, I2 is this concentration, HI is this concentration, then all we have to do is plug these numbers into our expression and solve for Kc, okay? So they've given us everything at equilibrium. So HI is this guy, so this is going to be on top, 0.78 molar squared divided by the concentration of H2, which is 0.11, and then the concentration of I2, which is also 0.11. So multiply, divide, we end up with a number of 50.3. And again, we're solving for a K. Just remember that K, regardless of what we put into it, right, we put molarities into it, K is unitless. It's always unitless. There's a reason for that we don't ever really talk about, but that's it. There's no units for K, so this is the magnitude of K. And again, you could look at this and say, well, actually, this reaction is probably product favored, right? So this probably products predominate at equilibrium because this thing is greater than 1. So K is greater than 1, which tells you that products are in greater supply at equilibrium comparatively to reactants. Okay, so again, that was the easy way to do this. Now we're going to go through the hard way. Okay, so the harder way is that you would be given all of the initial concentrations. Okay, so for a reaction, you would be able to control how much you put of everything in initially. So you know all initial concentrations. And then at the end of the reaction, when it has come to equilibrium, you would be capable of measuring one equilibrium concentration, right? So if you know all of the initial concentrations and you know one of the equilibrium concentrations, you will be able to determine the remainder of them from the initial concentrations and the stoichiometry of the reaction. So let me try to illustrate what I mean by that. So let's say that you have a reaction where you have A going to make 2B, okay? And in this scenario, you initially know, because you put it into the flask, that you have 1 molar of A and you have 0 of B. So the reaction has not begun, you have 0 product initially, okay? At equilibrium, once it's reached, you go back in and you measure the concentration of A to be 0.75, right? So you would be able to utilize all of this data to also determine the equilibrium concentration of B. Well, how would you do that? So we're going to introduce you here to an ICE table for the first time. So an ICE table we'll be using throughout the semester, right? ICE stands for Initial Change in Equilibrium, okay? So in this ICE table, we list our concentrations of our products and reactants up above. So we'd list it like we normally would in a chemical reaction. So we have our reactants. We then list our products, right? And you can usually denote that, be a nice little arrow, okay? And then for the initial, we'll write our initial concentration. So for this reaction, we initially had 1 molar and 0 molar, right? And then change is going to represent the change in going from initial to equilibrium. in equilibrium is going to be our equilibrium values. That's what the E stands for. So initial, change, and equilibrium, right? So for this problem, we knew initially this guy, we knew this guy, and then we knew one equilibrium value, which was this guy, right? So knowing that this went from 1 to 0.75, you can easily see that the change here is that it lost 0.25 molar, right? So the change is defined by what happened to it when it went from initial to equilibrium concentrations, right? But because of the stoichiometry, whatever happens to the reactant, double of it has to happen to the products, right? So if we lost 0.25 with respect to the reactants and going from initial to equilibrium concentrations, then the product is essentially going to have to gain 2 times 0.25, because again, for every one of these that we lose, we gain 2 B's, right? So then, once we do that, if it goes from 0 and it gains 0.5, then at equilibrium, it has a concentration of 0.5, okay? So again, I'm going to go through this in another problem to really kind of hit home how you're going to go about answering these types of problems. All right, so let's say that we have a different reaction. We have CO combining with hydrogen to form methanol, okay? And initially, we have a 0.5 molar CO concentration and a 1 molar hydrogen concentration, okay? At equilibrium, we come back in and we measure the concentration of CO, and that ends up being 0.15 molar. So what is the value of the equilibrium constant from this data? So one important thing to note is that they only give us initial concentrations of CO and H2, and that's on purpose, because the big idea behind this is that you're putting in only reactants initially, and the initial concentration of products can always be assumed. Let me reverse that. Can always be assumed CH3OH to be 0, right? You haven't started the reaction. All you have is reactants. You haven't made any products. So if they don't give you any type of concentration for products, you should always assume that they are 0 initially, okay? All right, so now we have all of our data. We're going to go ahead on the next slide and fill out an ICE table. So I've already drawn my little ICE table where I list my reactants. I also list it with their stoichiometry, so their stoichiometric coefficients. And so in this first little bit, I've listed out my I, my C, and my E, and I'm going to go ahead and fill in everything that I know up to this point. Okay, so I know that I have initially 0.50 molar of CO, and I have 1.00 molar of H2, and also initially I have 0 molar of products. That's what we can assume. And then at equilibrium, we have 0.15 molar of CO, okay? So first step in this is drawing your ICE table, and then listing the known initial concentrations as well as the one equilibrium concentration. Okay, so then what's next? So next, you're going to utilize the known, let me rewrite this guy. So we have 0.50 molar, we have 1, and we have 0, and then at equilibrium we have 0.15 molar, okay? So now in this next step, you're going to utilize the one difference between the initial and the equilibrium value to figure out what this change is, right? So in going from 0.5 to 0.15, how much should CO have to lose, right? So that's going to define our change here. So this ends up being a minus 0.35, right? So 0.5 minus 1.5 gives us minus 0.35. So to get from here to here, it had to have lost 0.35. Okay, so once that's defined, we can move on to helping to define all the other changes. Okay, so then, once we have this guy, we can use it, as well as the stoichiometry of the reaction, to determine the change for the other unknown things, right? So if CO lost 0.35 molar, then H2, which is also a reactant, also has to lose but it has to lose essentially twice that. Again, because for every one of these we use 2 of these. So this is going to be a change of 2 times 0.35 molar. And then for our product, we're not going to be losing stuff, we're going to be gaining, so we're going to represent that as a plus. And again, it's only a 1-to-1 relationship, so for every one of these we lose, we only make one of these, so it is going to gain the equivalent 0.35 molar amount, okay? So now we've used this first change, to define the changes for the other 2. And then the final step, we are going to sum each of the columns, right? So for the first column, this is already summed. 0.5 minus the change is 0.15. For the second column, 1 minus essentially a 2 times this, which ends up being a minus 0.70, gives us 0.30. So we're just summing the columns. So sum this column, and then 0 plus 0.35 gives us a 0.35, okay? So now we have our equilibrium concentrations for all of our reactants and products. The last step in this is going to be using those concentrations that we've just determined, plugging them into the equilibrium constant expression, and then determining the equilibrium constant from that. Okay, so our equilibrium constant expression is Kc. Why is it doing this? So Kc is equal to the concentration of CH3OH over the concentration of CO times H2 squared. So again, this is the equilibrium constant expression. Anytime I'm asking for an expression, this is what I want to see essentially. So now we're going to go ahead and plug in those values. So for methanol, we had 0.35. For CO, we also have 0.35. And then for H2, we had 0.3 squared. So we multiply, we divide. Oh, no, that wasn't 0.35. This guy was wrong, sorry. This was the one that we were given. We had 0.15 at equilibrium. Okay, so then multiply, divide. We end up with an equilibrium constant, again, are equal to 25.9. So this is what our equilibrium constant is equal to. And again, you would predict that products would predominate at equilibrium because this equilibrium constant is larger than 1. Okay, so similar type question, except we have new reactants, new products. So we have this reaction. Initially, again, it only has reactants, right? It only has the CH4. So you can assume that the concentration of both the products initially, so C2, H2, as well as H2, are both equal to 0. And so then I want to know, after we reach equilibrium, you have a C2H2 concentration of 0.035. What is the value of the equilibrium constant? So this is the exact same type of problem. This will be on the video assignment quiz, so make sure that you do this correctly and do it maybe before you go on so you don't run out of time. Okay, so last little bit, we're going to talk about something called the reaction quotient. Okay, so we've been looking at the law of mass action with respect to equilibrium, right? So we have defined, how do we determine what K is? Well, K is just the concentration of products over the concentration of reactants at equilibrium, most importantly. And again, these are going to be raised to their stoichiometric coefficients, right? The big thing about this, though, is that if we are determining K, that these guys have to be at equilibrium. You cannot plug them in to determine K if they are not at equilibrium, okay? So what if they aren't at equilibrium and we do go ahead and plug them in? Are you going to like violate some terrible rule? So no, you're not. But what you have to realize is that if you are plugging in concentrations that aren't at equilibrium, you're instead calculating what is called the reaction quotient, which we give this little letter Q. Okay, so Q is the exact same thing as K, right? It is the law of mass action. So products divided by reactants, right? If you're using concentrations, we call this QC. Same thing. If you're using partial pressures, we call it QP. What is the purpose of Q, though? So Q is going to help us determine where we are relative to equilibrium, okay? So all reactions are going towards equilibrium. You start them, they're going to move towards a state of equilibrium, okay? Depending on where it's at, is going to depend on whether or not it needs to make more products to get to equilibrium or it needs to make more reactants, okay? And we're going to talk about doing things called shifting left or shifting right, depending on where it needs to go to get to equilibrium, okay? So how are we going to go about thinking about this? So I'm going to Okay, so then what is the purpose of Q, the reaction quotient? How are we going to use it? Again, it's going to tell us where we're at in a reaction relative to K, right? So what do we mean by that? So let's take a couple of extreme situations to kind of illustrate how we calculate Q and how that's going to lead us to know where the reaction is going to go to get to K. Okay, so let's start out with one extreme where we only have reactants in our flask, okay? Okay, so let's imagine that we'll just illustrate this guy as reactants will be our R, and then it's going to make products, which is our P, okay? And so initially, we only have stuff for R. Let me draw that better. So initially, we only have reactant concentrations. Let's imagine they're 1 molar, and we don't have any product concentrations. Let's imagine they're 0, okay? So we can plug in our concentrations into our law of mass action, right? Again, we would be calculating Q here. So let's say that the equilibrium constant for this reaction ends up being something like 100, okay? So we know we're calculating Q because right now our ratio of products of reactants is not equal to 100. It is equal to something less than 100, right? So when we plug this in, we'll have zeros for our products. We'll have, let's say, 1 for our reactants. And so 0 divided by anything is always equal to 0, okay? So right now, Q is 0, K is 100. So Q is less than K, right? How does this reaction need to shift to get to K? That's the big question. Well, obviously, we don't have any products at this point in time, right? So the products are in our numerator, and the reactants are in our denominator. And again, this ratio at this point in time is too small, right? So one way that we can increase it to get to K is we can increase the concentration of our numerator. So we make more products. We could decrease the concentration of our denominator so we can use more reactants. And so we call that shifting right. So right now we need to shift to the right. We need to make more products, use more reactants to get this Q, which is less than K, to K, okay? So if Q is less than K, what is the reaction going to do? It's going to shift to the right to get to equilibrium. It's going to make more products. It's going to use more reactants, okay? On the other side of the coin, we can look at the other extreme. Let's say we start with only products, so no reactants. So again, if we have our little hypothetical concentrations, we would have a 0 for our reactants, and for our products, let's just imagine something like 1, okay? We're dealing with the same exact K. K is equal to 100. So if we plug in these values, we'd have something like 1 for our products on top. We'd have 0 for our reactants on bottom. And again, anything divided by 0 is equal to infinity, okay? So right now, relative to K, Q is much greater than K. So in a situation where we start with only products, we are away from equilibrium, we want to know where we're going, well, our Q is much larger than K. So what needs to happen to get to K, which again is equal to 100? If it's too big, then that means that the numerator needs to decrease. We need to decrease the product concentrations. The denominator needs to increase, right? So this guy needs to decrease, denominator needs to increase to get this ratio to be a smaller value to get it back to K. And so what does that mean in terms of the actual chemical reaction? So we would call something like this, instead of shifting right, we need to shift left. So shifting left means we're going to use products, we're going to make more reactants to get back to equilibrium, right? Our numerator is too big, the products are too much, our denominator is too small, the reactants are too few, we need to make more reactants, so we're going to shift left, okay? And then there's a special situation where we have Q, when we have equal reactant and product concentrations, that just gives us a Q of 1. I don't even know why I've included this on this slide at this point. But yeah, if you have equal product and reactant concentrations, then your Q is going to be equal to 1. Okay, so overall, how is Q, the reaction quotient, going to help us determine what's going to happen in a reaction? So I like to kind of consider this like a number line, right? So in a number line, we'll put K as some sort of central guy. So again, let's say K is 100, right? So if Q is less than K, so if Q is down here at some point in time less than K, then to get to K, the reaction is going to shift right? If it shifts right, it's going to make more products, it's going to use more reactants, right? On the other hand, if Q is greater than K, then the reaction needs to shift back to the left, needs to go left, it needs to use products, make more reactants, okay? So depending on where Q is relative to K, should be able to help you predict what the reaction is going to do. Is it going to shift to the right, make more products, or is it going to shift to the left, make more reactants? So how would you actually utilize this in a problem? So for example, they give us a reaction here. We have N2O4 going to make 2 NO2s, and they tell us what the equilibrium constant is for this reaction. Then they say, okay, we have a reaction, and we have at some point in time a concentration of 0.0255 for our product and 0.0331 for our reactant. Number one, they want us to calculate this ratio, the law of mass action. They want us to calculate the reaction quotient and determine whether the reaction will shift to the left or shift to the right. So which reaction or which direction will the reaction proceed, okay? So to do that, I'm just going to go ahead and write out my reaction quotient expression. So this is QC is equal to NO2 squared divided by concentration of N2O4. And again, why do I know that this isn't K? Why am I not putting a K here, even though it's the exact same expression? It's because we're not at equilibrium, okay? If these concentrations were at equilibrium, then we would be calculating K, but they are not, so we're calculating Q. Okay, so then I'm going to go ahead and plug everything in. I get 0.0255 squared divided by 0.0331. And so when I multiply those guys out and I divide them, I get a ratio of, where did it even go? 0.0196. Okay, so that's where we're at. That's what Q is equal to. So Q is equal to 196, okay? And again, K here is equal to 5.85 times 10 to the minus 3. So now, which way will this reaction shift? Is Q less than K, or is Q greater than K? So it may be a little bit easier if I wrote this out of scientific notation, 0.00585. So hopefully you should be able to see right now that Q is greater than K, right? And so to get to K, it needs to decrease its value. It needs to decrease that ratio, meaning that it needs to use more product, make more reactant, right? So Q is greater than K, and so where is it going to go? Well, it's going to shift left. Oh, that's really ugly. I'm getting towards the bottom of this Why is this not talking to me? Getting towards the bottom of this page. So it needs to shift left. It needs to make more reactants. Use products. And again, that's because Q at this point in time is greater than K. That ratio is too large. Again, if I drew out my little number line, here's K, here's Q. How does it get back? Well, it goes left. Okay, so again, I'll probably have a type of problem just like this, maybe a little bit easier to see, but you should be able to utilize the Q expression to determine Q, to be able to know where is the reaction going to go relative to where it wants to get, which is equilibrium.